Picture this: you're staring up at the night sky, convinced that the dark side of the moon never sees sunlight, just like your favorite sci-fi movies showed you. But what if I told you everything you thought you knew about space might be completely wrong? Welcome to a cosmic reality check, where we're dismantling 30 of the most stubborn space myths that even smart people fall for. From black holes that aren't actually cosmic vacuum cleaners to the shocking truth about boiling blood in space, we've got myth-busting revelations that will flip your universe upside down. Stick around, because by the end of this journey, you'll never look at the night sky the same way again, and that famous moon landing footage. Let's just say you'll finally have the receipts to shut down those conspiracy theories for good. Ready to have your mind launched into orbit? Let's blast off. Now let's tackle one of the most persistent space myths out there, the idea that humans never actually landed on the moon. It's time to unpack this conspiracy theory piece by piece with cold, hard facts. First, where did this myth even come from? The skepticism started bubbling up shortly after the Apollo 11 landing in 1969. Some folks pointed to oddities in the footage, like the flag appearing to wave in a vacuum or the lack of stars in photos, as supposed proof of a studio setup. But here's what science has to say about those claims. The flag only appeared to wave because it had a horizontal rod to keep it unfurled in the moon's airless environment. When astronauts moved it, the fabric kept vibrating due to inertia, creating that waving effect. As for the missing stars, camera settings on the lunar surface were adjusted to capture the bright lunar landscape, making stars too faint to appear. But the real nail in the coffin for moon landing deniers comes from technology we can actually test today. Astronauts left behind retroreflectors, mirror-like devices on the moon's surface during multiple Apollo missions. Scientists on Earth regularly bounce lasers off these reflectors to measure the moon's distance with pinpoint accuracy. No studio set could account for this ongoing scientific practice that's been happening for decades. Then there's the mountain of physical evidence. Hundreds of pounds of moon rocks were brought back, rocks that have been analyzed by scientists worldwide and found to be chemically distinct from anything on Earth, with features only possible from formation in an airless environment. Even Russia, America's space race competitor, confirmed these samples were genuine. Perhaps most convincing are the astronaut testimonies themselves. The 12 men who walked on the moon maintained identical stories under intense public scrutiny for their entire lives. Not one ever broke ranks despite enormous pressures and incentives to do so. Their accounts match perfectly with mission data, photographs, and independent tracking from other countries. So why does this myth persist? Human psychology loves a good conspiracy. It's more exciting than admitting hundreds of scientists and engineers pulled off one of history's greatest achievements through meticulous work. But when you examine the overwhelming physical evidence, continuing technical verification, and complete lack of credible whistleblowers after 50 years, the truth becomes crystal clear. That grainy footage we all know, it's not just real, it's one of humanity's proudest moments, preserved forever in the lunar dust. Now, shifting gears to another widely believed myth, the idea that the Great Wall of China is the only human-made structure visible from space. This claim has been repeated so often that it's practically ingrained in pop culture. But let's set the record straight with some orbital reality. First, where did this myth originate? It likely stems from a mix of exaggeration and old assumptions about the wall's sheer size. Stretching over 13,000 miles, it's undeniably massive, but visibility from space depends on far more than just length. The truth, from low Earth orbit where most crewed missions like the International Space Station operate, the Great Wall is incredibly difficult to spot with the naked eye. Astronauts, including NASA's own Chris Hadfield, have confirmed this firsthand. Hadfield famously noted that while the wall is long, Its narrow width and colors blending into the natural terrain make it nearly indistinguishable from surrounding features like rivers or roads. Here's the science behind why. To be visible from orbit, an object needs sufficient contrast with its surroundings. The Great Wall's materials, stone, earth, and brick, often match the tones of the landscapes it traverses. Compare that to sprawling urban areas or massive dams, which reflect light differently and can stand out more clearly. Even the pyramids of Giza, another oft-cited example, are easier to spot under the right lighting conditions because of their angular shapes and shadows. But what about higher altitudes like the Moon? The idea that the wall is visible from there is pure fiction. Astronauts who have walked on the lunar surface, like Alan Bean of Apollo 12, clarified that no human-made structures are discernible from that distance. At 240,000 miles away, Earth appears as a tiny blue marble continent and oceans are barely visible, let alone a narrow wall. The math simply doesn't add up. The wall's width would need to be hundreds of miles thick to resolve as even a single pixel in a lunar view photo. So why does this myth endure? It speaks to our fascination with human achievement. We want to believe our creations loom large enough to be seen from the cosmos. But the reality is humbling and enlightening. From space, what truly stands out are Earth's natural wonders. Hurricanes swirling over oceans, the green pulse of the Amazon, or the vast glow of city lights at night. The Great Wall's invisibility from orbit doesn't diminish its grandeur. It's a testament to how delicate human marks are on the scale of our planet, let alone the universe. Up next, we'll tackle another sound-related misconception, the eerie silence of space. Spoiler, it's not as quiet as you might think. Now, let's turn our attention to a myth that's as pervasive as it is poetic, the idea that space is utterly silent. Hollywood loves to show the vacuum of space as a vast, soundless void, but the truth is far more fascinating. Here's the science behind why space isn't as quiet as you've been led to believe. First, let's break down why sound, as we experience it on Earth, can't travel in space. Sound waves need a medium like air, water, or even solid objects to vibrate and carry energy. In the near-perfect vacuum of space, there's no air, no molecules to bump into each other, and thus no way for traditional sound to propagate. That's why astronauts can't chat without radios, and why explosions in movies like Star Wars would actually be eerily mute in reality. But silence isn't the same as absence of sound. While you wouldn't hear a supernova blast or a spaceship zooming past, space is alive with other forms of sound, just not the kind our ears can detect. Take planets, for example. Jupiter's magnetosphere, a swirling magnetic field, emits intense radio waves that scientists have converted into audible frequencies. The result, a haunting chorus of clicks, whistles, and crackles, almost like an interstellar ghost whispering through static. NASA's Juno mission captured these emissions, revealing a symphony of charged particles dancing along Jupiter's magnetic line. Then there's the cosmic microwave background, the faint afterglow of the Big Bang. While it's not sound in the traditional sense, this radiation permeates the universe, a low hum of energy that astrophysicists describe as the universe's oldest noise. It's like hearing the echo of creation itself, stretched across billions of years. Black holes, too, defy the myth of silence. In 2003, astronomers discovered something extraordinary: pressure waves rippling through the superheated gas around the Perseus galaxy cluster's central black hole. These waves, translated into sound, produce a note 57 octaves below middle C, a cosmic bass so deep it's more felt than heard. Imagine the lowest pipe organ note, then drop it into a well the size of a galaxy. So why does the silent space myth persist? It's a mix of Hollywood dramatization and our own earth-bound intuition. We're so used to sound being tied to our immediate environment that it's hard to grasp the idea of hearing the universe in unconventional ways. But the reality is that space does have a voice, it just speaks in frequencies we've had to learn to translate. Coming up, we'll shatter another colorful illusion, the belief that the sun is yellow. Hint, your childhood drawings got it wrong. Now, let's tackle a myth that's as bright as it is misleading, the idea that the sun is yellow. If you've ever reached for a yellow crayon to draw the sun, you're not alone, but science tells a very different story. The truth is, our star is actually white, and the reason it often appears yellow has everything to do with the way light travels through Earth's atmosphere. Here's how it works. The sun emits light across the entire visible spectrum, blending all colors to produce what our eyes perceive as white. But when that sunlight enters Earth's atmosphere, it collides with molecules and tiny particles, scattering shorter wavelengths like blue and violet more easily than longer wavelengths such as red and yellow. This phenomenon, called Rayleigh scattering, is the same reason our sky looks blue during the day. The scattered blue light gets dispersed in all directions, while the remaining light, now leaning toward yellow and red, reaches our eyes directly. That's why the sun often takes on a golden hue near sunrise or sunset, when sunlight has to pass through even more of the atmosphere. But the sun's true color becomes obvious when you leave Earth behind. Astronauts and satellites observing from space describe it as a blinding white disk with no hint of yellow. Spectral analysis confirms this. By breaking sunlight into its component wavelengths, scientists can see that the sun's peak emission falls squarely in the green part of the spectrum. But because it emits so much light across all colors, the overall blend registers as white to human vision. So why does the myth persist? Part of it is cultural. From children's drawings to weather icons, yellow has become shorthand for the sun, reinforcing the misconception. Even photography plays a role. Cameras often adjust white balance to make sunlight appear warmer, enhancing the yellow tones we've come to expect, but the science doesn't lie. If you could safely stare at the sun from space, you'd see its true color, a brilliant, unfiltered white. Next up, we'll confront a chilling myth about what happens to the human body in the vacuum of space. Spoiler, it's not the explosive Hollywood scenario you might imagine. Now, let's shift gears to a myth that's straight out of a sci-fi nightmare, the idea that humans explode when exposed to the vacuum of space. Hollywood loves this dramatic image, but the reality, while still deadly, is far less explosive. Here's what actually happens. In 1965, NASA conducted a chilling experiment when a technician inside a vacuum chamber accidentally had his suit depressurized for about 15 seconds. Instead of bursting like a balloon, he remained intact, though he later reported feeling saliva boiling on his tongue before losing consciousness. This harrowing incident gives us a glimpse of the real effects of space exposure. The truth is, your body wouldn't explode because human skin is surprisingly tough. It's elastic enough to contain your internal pressure, even in a vacuum. But that doesn't mean space is safe. Without atmospheric pressure holding your fluids in check, your blood would start to vaporize, and your lungs would rapidly collapse as the air inside them expands. You'd likely pass out within 15 seconds due to oxygen deprivation, and after a minute or two, irreversible damage would set in. Another key factor is temperature. Space isn't uniformly cold, it's just an absence of matter to conduct heat. So while you wouldn't instantly freeze, you would lose heat slowly through radiation. The bigger danger is the lack of oxygen and pressure, not Hollywood's cartoonish explosions. So why does the exploding myth persist? It's visually dramatic, and movies thrive on spectacle. But real space accidents, like the tragic Soyuz 11 mission where 3 cosmonauts died from rapid decompression, show a much quieter yet equally fatal scenario. Their cabin lost pressure during re-entry, and while they didn't explode, they succumbed to suffocation before they could react. Next, we'll unravel another lunar misconception, that the so-called dark side of the moon is always shrouded in darkness. The truth is far more interesting. Now, let's shed some light on one of the moon's most misunderstood features, the so-called dark side. despite its ominous nickname, the far side of the moon isn't actually a shadowy wasteland. In reality, it gets just as much sunshine as the side we see from Earth. So how did this myth take hold? It all comes down to a simple mix-up between darkness and visibility. Here's the truth. The moon is tidally locked to Earth, meaning it rotates on its axis at the same rate it orbits our planet. That's why we always see the same familiar face, the near side. But while the far side remains hidden from our view, it's not permanently dark. In fact, over the course of a lunar month, every part of the moon experiences day and night cycles, each lasting about 2 Earth weeks. During a new moon, when the near side is dark, the far side is bathed in sunlight, and vice versa during a full moon. This misconception likely stems from the term dark side, which sounds more mysterious than scientific. Even Pink Floyd's iconic album, The Dark Side of the Moon, cemented the idea in pop culture, but scientists prefer calling it the far side to avoid confusion. The first images of this elusive hemisphere came from the Soviet Luna 3 probe in 1959, revealing a landscape surprisingly different from the near side, more rugged, with fewer of the smooth plains we call Maria. To visualize tidal locking, imagine holding a ball on a string and spinning around. If the ball spins exactly once per revolution, you'll always see the same side of it, just like Earth and the moon. But sunlight doesn't play favorites. As the moon orbits, the sun illuminates different regions, creating phases we see from Earth. When we see a crescent moon, the far side is nearly fully lit. The Apollo missions gave astronauts a unique perspective. Those who orbited the moon, like the Apollo 8 crew, witnessed the far side in person, a sunlit terrain untouched by Earth's glare. Modern missions like China's Chang'e 4 have even landed there, proving it's anything but perpetually dark. So next time someone mentions the moon's dark side, you'll know the real story. It's not a land of eternal night, just a hemisphere that likes to keep its distance. Up next, we'll tackle another cosmic mix-up, the idea that there's no gravity in space. Trust me, you'll want to stick around for this one. Now, let's clear up one of the most persistent misconceptions about space, the idea that there's no gravity up there. If you've ever seen astronauts floating inside the International Space Station, you might assume they're in a zero-gravity environment. But here's the twist: gravity doesn't just vanish when you leave Earth. In fact, it's very much present in space, and it's the reason planets orbit the Sun and the Moon circles Earth. So why do astronauts appear weightless? The answer lies in a phenomenon called microgravity, and it's all about motion, not the absence of gravity. Picture this: the International Space Station orbits Earth at roughly 400 kilometers above the surface. At that altitude, Earth's gravity is still about 90% as strong as it is on the ground. But the ISS isn't just sitting still, it's moving forward at an incredible speed, around 28,000 kilometers per hour. This creates a constant state of free fall toward Earth. But because the station is also moving sideways so fast, it keeps missing the planet. The result? A perpetual fall that gives astronauts the sensation of weightlessness. It's like being on a roller coaster that's always dropping, except this one never hits the bottom. Scientists call this environment microgravity because the effects of gravity aren't gone, they're just balanced by the station's motion. The term zero gravity is a bit misleading, but it's stuck because it's easier to say. Inside the ISS, everything from floating pens to water droplets forming perfect spheres behaves as if gravity has disappeared. But if you could magically stop the station's orbital speed, gravity would immediately pull it back to Earth. This delicate balance is why astronauts train in special aircraft nicknamed vomit comets. These planes fly in parabolic arcs, creating short periods of weightlessness by mimicking free fall. It's the closest you can get to space conditions without leaving the atmosphere. And if you've ever seen videos of astronauts training underwater, that's another clever simulation. Neutral buoyancy in water approximates microgravity, helping astronauts practice spacewalks and equipment handling. Gravity's reach is far more extensive than most people realize. Even the Moon, which is nearly 400,000 kilometers away, feels Earth's pull. That's what keeps it in orbit. The same goes for the ISS. Without gravity, it would fly off into space in a straight line. So the next time you see astronauts floating, remember, they're not beyond gravity's grasp. They're racing around the planet so fast that they're forever falling without ever landing. Up next, we'll explore another cosmic illusion, the asteroid belt. You might be surprised to learn how empty it really is out there. Now, let's tackle a Hollywood-fueled myth that makes space seem far more crowded than it really is: the idea that the asteroid belt is a chaotic field of rocks smashing into each other like some cosmic bumper cars. Movies and TV shows love to depict spaceships weaving through a dense maze of asteroids, dodging disaster at every turn. But here's the reality: the asteroid belt is overwhelmingly empty. In fact, if you were standing on one asteroid, your chances of seeing another with the naked eye would be almost zero. So how empty are we talking? Picture the asteroid belt as a vast highway circling the Sun between Mars and Jupiter. Spread across this enormous region are millions of asteroids, but they're spaced so far apart that the average distance between them is around 1 million kilometers. That's more than 2.5 times the distance from Earth to the Moon. Even the largest asteroid, Ceres, which makes up a third of the belt's total mass, is a tiny dot in this expansive desert. To put it another way, if you combined all the material in the asteroid belt, it would still be less than 4% of the Moon's mass. Scientists have sent spacecraft through the belt multiple times, like NASA Pioneer and Voyager missions, and not once have they had to dodge asteroids. The odds of a collision are astronomically low. When the Dawn probe visited Ceres in 2015, it didn't encounter a single asteroid along the way. That's how sparse this region truly is. But why the misconception? Part of it comes from how we visualize space. In diagrams, asteroids are often shown as tightly packed dots for simplicity, giving the illusion of density. The truth is far less dramatic. Most asteroids are tiny, some no bigger than a pebble, and they're scattered so widely that you'd have to aim carefully just to find one. Even the so-called Kirkwood gaps, regions where Jupiter's gravity has cleared out asteroids, add to the emptiness. Here's a fun fact: if you could stand on an asteroid and look around, you'd see more stars than rocks. The belt isn't a danger zone. It's a quiet, lonely stretch of space where each asteroid follows its own uneventful orbit. Next time you see a movie scene with a ship narrowly avoiding asteroid collisions, remember, the real challenge wouldn't be dodging rocks. It'd be finding one in the first place. Up next, we'll debunk another cosmic twin story. Venus and Earth might share a nickname, but their realities couldn't be more different. Now, let's unravel the myth that Venus and Earth are twin planets. While they're often called siblings due to their similar size and distance from the Sun, the resemblance ends there. Venus is a hellish world with conditions so extreme they'd make Earth's worst weather seem like a breeze. First, let's talk about Venus's atmosphere. While Earth's air is a life-giving mix of nitrogen and oxygen, Venus is wrapped in a thick blanket of carbon dioxide with clouds of sulfuric acid. The pressure on its surface is 90 times heavier than Earth's, equivalent to being nearly 1 kilometer underwater. And if that's not suffocating enough, temperatures there soar to 460 degrees Celsius, hot enough to melt lead. This runaway greenhouse effect turned Venus into the solar system's hottest planet, even though Mercury is closer to the Sun. Meanwhile, Earth's atmosphere is a delicate balancing act. Our greenhouse gases trap just enough heat to keep oceans liquid and life thriving, without tipping into a Venus-like inferno. But Venus lost that balance long ago. Scientists believe it might have once had oceans, but as the Sun grew brighter, Its water vapor intensified the greenhouse effect, boiling away its seas and leaving behind a barren, scorched landscape. Then there's the sky itself. On Earth, sunlight filters through blue skies, but Venus's dense atmosphere bends light so intensely that the sun would appear as a faint, diffused glow, if you could even see it through the perpetual acid clouds. And while Earth's day-night cycle brings predictable changes, Venus spins so slowly that a single day lasts longer than its year. Even their geological stories diverge. Earth's surface constantly renews through plate tectonics, while Venus seems to have sporadic, catastrophic resurfacing events, where lava floods vast regions in short bursts. So why the twin myth? It's mostly because of their similar size and rocky composition. But in reality, Venus is a cautionary tale of what happens when a planet's climate spirals out of control. It's not Earth's twin. It's more like a twisted mirror image showing us how lucky we are to have a world with breathable air, temperate climates, and the right conditions for life. Next up, we'll tackle another cosmic mystery, the idea that black holes are relentless vacuum cleaners sucking in everything around them. But as you'll see, science tells a far more fascinating story. Let's turn our attention to another widely misunderstood cosmic phenomenon, the idea that black holes act like cosmic vacuum cleaners, endlessly devouring everything in their path. While they are certainly powerful, the reality is far more nuanced and fascinating than sci-fi portrayals suggest. First, let's break down what a black hole actually is. At its core, a black hole is an object so dense that its gravitational pull becomes irresistible once you cross a point called the event horizon. Think of the event horizon like a one-way door. Once matter or light passes through, there's no turning back. But here's the key: black holes don't suck things in like a vacuum cleaner. Instead, their gravity behaves just like any other massive object in space, whether it's a star or a planet. Imagine dropping a marble onto a trampoline with a bowling ball in the center. The marble will roll toward the bowling ball because of the dent it creates. That's gravity. Now replace the bowling ball with something far heavier, like a cannonball. The dent becomes steeper and the marble rolls in faster. A black hole is like the cannonball, warping space-time so intensely that near its event horizon, even light can't escape the curve. But outside that boundary, objects can orbit a black hole just like planets orbit the sun. In fact, astronomers have observed stars whipping around the supermassive black hole at the center of our galaxy, completely unharmed as long as they keep their distance. So why the misconception? Part of it comes from their name. Black hole sounds like an endless pit, but another reason is how we visualize them. Movies often depict black holes as swirling vortexes pulling in stars and spaceships. In reality, a black hole's gravitational influence follows the same rules as any other object. If our sun magically turned into a black hole of the same mass, don't worry, it won't. Earth's orbit wouldn't change, we'd just freeze in the dark. The truth is, black holes are messy eaters. Matter falling toward them often forms an accretion disk, a spinning ring of superheated gas and dust. Friction within the disk heats it to millions of degrees, creating some of the brightest objects in the universe, like quasars. But most material never makes it past the event horizon. Instead, intense magnetic fields and radiation can blast it back into space, sometimes forming powerful jets that stretch for thousands of light years. Black holes aren't lurking monsters waiting to consume the cosmos. They're extreme laboratories where gravity reveals its wildest behaviors. And far from being vacuum cleaners, they're more like cosmic recyclers, shaping galaxies and sparking new star formation with their leftovers. Next, we'll challenge another myth, this time about human behavior and the moon's supposed influence on us. You might be surprised by what science says. Now, let's tackle a myth that's been woven into folklore for centuries, the idea that the moon, especially when it's full, has a mysterious power over human behavior. You've probably heard the tales. Emergency rooms get busier, crime rates spike, and people act a little more unpredictably under its glow. But here's the reality: science has looked hard at these claims, and the evidence just doesn't hold up. First, let's address the so-called lunar effect head-on. The belief dates back to ancient times, linking the moon's phases to everything from madness, hence the word lunatic, to fertility cycles. Even today, some nurses, police officers, and teachers swear they notice patterns tied to the full moon. But when researchers dive into the data, something fascinating happens. Study after study, analyzing everything from crime reports to hospital admissions, psychiatric episodes to animal bites, finds no significant correlation between the moon's phase and human behavior. Take a landmark study published in the journal Psychological Bulletin, which reviewed over 100 lunar effect studies. The conclusion: there's no consistent statistical evidence linking the full moon to increases in erratic behavior, crime, or medical emergencies. Another sweeping analysis of psychiatric hospital admissions across multiple countries found zero uptick during full moons. Even animal shelters report no rise in dog bites, despite the myth that pets act out more under a full moon. So why does the myth persist? Part of it comes down to cognitive bias, our brains love patterns. If a nurse has one unusually chaotic shift during a full moon, they're more likely to remember it and attribute it to the moon, while forgetting the dozens of other full moons that passed without incident. Confirmation bias keeps the legend alive even when the numbers disagree, but there's another layer here. The moon does influence Earth in profound ways, just not human minds. Its gravity creates tides, stabilizes our planet's axial tilt, and even subtly affects some animal behaviors like coral spawning. Yet when it comes to humans, the moon's pull is purely poetic, not physiological. Your sleep might feel slightly different during a full moon. Some studies suggest melatonin levels dip, but the effect is minuscule compared to factors like caffeine or screen time. Ultimately, the moon's magic lies in its ability to inspire, not control us. It's a beacon for artists, dreamers, and scientists alike. But if you're blaming your bad day on the full moon, you might want to look a little closer to home. Up next, we'll take on a financial myth about space exploration specifically, the idea that NASA budget is astronomical. You might be shocked by how the numbers really stack up. Now, let's shift our focus to a myth that often stirs up heated debates: the idea that NASA budget is some kind of cosmic money pit. You've probably heard the complaints: why spend billions on space when we have problems here on Earth? But here's the thing: when you actually look at the numbers, NASA funding isn't just modest, it's downright humble compared to other government spending. First, let's put the numbers in perspective. NASA annual budget hovers around $25 billion. That might sound like a lot, but consider this: the United States spends over $800 billion on defense each year. That means NASA's entire budget is less than 0.5% of the military's. To put it another way, for every dollar in the federal budget, NASA gets roughly half a penny. Even the National Park Service, with its $13 billion budget, isn't far behind NASA in funding. But the myth persists because space exploration feels expensive. When we hear about a multi-billion-dollar Mars rover or a moon mission, it's easy to assume NASA is soaking up taxpayer dollars. What often gets left out of the conversation is the return on investment. Every dollar spent on NASA doesn't just vanish into space, it fuels technological breakthroughs that trickle down to everyday life. Memory foam in your mattress, scratch-resistant lenses in your glasses, even the camera in your smartphone, all owe their existence to NASA research. And let's talk about jobs. NASA budget supports tens of thousands of high-paying engineering, scientific, and manufacturing jobs across the country. Private companies like SpaceX and Blue Origin have also flourished thanks to NASA contracts, creating even more economic ripple effects. When you factor in the spin-off technologies and the industries they've spawned, NASA budget starts looking less like an expense and more like a seed planted for future growth. Now here's where the myth really falls apart. Adjusted for inflation, NASA's budget today is just a fraction of what it was during the Apollo era in the 1960s. Back then, NASA consumed over 4% of the federal budget. Today, it's around 0.4%. Yet despite this shrinking slice of the pie, NASA has delivered breathtaking achievements, landing rovers on Mars, probing the outer solar system, and launching the James Webb Space Telescope to peer back in time at the early universe. So why does the myth of NASA's massive budget endure part of its visibility? Space missions are flashy and make headlines, while other far costlier programs operate in the background. But the bigger reason might be perspective. When people hear billions, they imagine a bottomless vault of spending, not realizing that in the grand scheme of government budgets, NASA's share is more like spare change. Next up, we're turning to a myth that's literally cooler than it seems, the idea that meteorites land scorching hot. You might be surprised by what scientists have discovered about these cosmic visitors. Let's tackle another fascinating space myth this time about meteorites. You've probably seen movies where a flaming space rock crashes to Earth, sending up plumes of smoke and leaving a sizzling crater. It's a dramatic image, but here's the reality. Most meteorites land surprisingly cold. So why the misconception? It all comes down to what happens when a meteoroid, the term for the rock while it's still in space, enters Earth's atmosphere. As it plows through the air at tens of thousands of miles per hour, the friction heats its surface to thousands of degrees, creating that iconic fiery streak we call a meteor. But here's the twist: that heat doesn't penetrate deeply. The outer layer vaporizes in a process called ablation, effectively acting like a heat shield for the interior. Think of it like an ice cube skimming a hot pan. The outside melts instantly, but the core stays frozen. By the time the meteoroid slows down enough to survive the fall, now called a meteorite, it's often no hotter than a warm stone. In fact, many meteorites are found covered in frost or even embedded in ice. One of the most famous examples is the Peekskill meteorite, which landed in New York in 1992. Witnesses described it as warm to the touch, not scorching. Even more telling, the Allende meteorite, which fell in Mexico in 1969, was recovered so quickly that some pieces were still cold enough to condense moisture from the air, leaving them damp. But wait, what about those reports of smoking meteorites? That's usually just steam. When a cold rock lands in damp soil or snow, the temperature difference can create a brief mist like breath on a winter morning. And while larger meteorites can retain some heat from their fiery descent, it's rarely enough to be dangerous. Scientists handling newly fallen meteorites often pick them up barehanded without issue. The real kicker: some meteorites are colder than their surroundings. In Antarctica, where thousands of meteorites are preserved in ice, these space rocks often sit at sub-zero temperatures for millennia before discovery. So next time you see a Hollywood meteorite melt through a sidewalk, remember, in reality, you'd have better luck chilling your drink with one than starting a fire. Now let's turn our attention to another celestial mix-up, the idea that the North Star is the brightest in the night sky. Turns out, there's a much more luminous contender stealing its spotlight. Moving on to another starry misconception, let's set the record straight about the North Star. Many people assume Polaris, our trusted North Star, is the brightest beacon in the night sky, but that title actually belongs to others. First, meet Sirius. This dazzling star, part of the constellation Canis Major, outshines Polaris by a landslide. In fact, Sirius is the brightest star visible from Earth, glowing with a brilliance nearly 25 times that of our Sun. Its name even means scorching in Greek, a nod to its fiery appearance. Then there's Vega, the gem of the Lyra constellation, which also steals the spotlight from Polaris. Vega isn't just brighter, it's a celestial rock star spinning so fast it bulges at its equator and serving as a key reference point for astronomers. So why does Polaris get all the attention? It's not about brightness but reliability. Polaris sits almost directly above Earth's North Pole, making it a fixed point in the sky while other stars appear to circle around it. For centuries, navigators and explorers from ancient Polynesian voyagers to European sailors used Polaris as a guide. If you can spot it, you've found true north. But here's the twist: Polaris isn't even in the top 40 brightest stars. It's like comparing a steady flashlight to a stadium light. One's dependable, the other's dazzling. Polaris has another quirk. It's not a single star, but a trio. The main star, Polaris A, is a supergiant with two smaller companions orbiting it. And while it's been our celestial anchor for generations, it won't hold the title forever. Due to Earth's wobbly axis called precession, the role of North Star will eventually pass to Vega in about 12,000 years. So the next time you gaze up at the night sky, remember, brightness doesn't always mean importance. Polaris might not win a beauty contest against Sirius or Vega, but its steadfastness has guided humanity for millennia. Now, let's shift our gaze to another cosmic. Mix up the idea that space travel leaves you completely weightless. The truth, you're in for a floating surprise. Now, let's untangle another cosmic illusion, the idea that astronauts float in space because there's no gravity. This myth is so pervasive, even blockbuster movies get it wrong. The truth, gravity is very much at work up there. Take the International Space Station, for example. It orbits Earth at an altitude of around 250 miles. At that height, Earth's gravitational pull is still about 90% as strong as it is on the surface. So why do astronauts appear weightless? The answer lies in a concept called microgravity, specifically free fall motion. Imagine tossing a ball straight ahead. It arcs downward because gravity pulls it toward Earth. Now, imagine throwing it so fast that Earth's surface curves away at the same rate the ball falls. That's essentially what's happening with the ISS. The station is constantly falling toward Earth, but it's also moving forward at roughly 17,500 miles per hour, so fast that it keeps missing the planet. Astronauts inside are falling at the same rate, creating the illusion of zero gravity. This delicate balance is why the ISS doesn't need engines to stay in orbit. It's in a perpetual state of free fall, like a roller coaster cresting a hill, except the hill never ends. But don't confuse this with actual weightlessness. If gravity vanished, the ISS would fly off into space in a straight line. Instead, Earth's pull keeps it tethered in a curved path, a dance between inertia and gravity. Here's another twist: microgravity isn't perfect. Tiny forces like atmospheric drag or the station's own vibrations create minute accelerations. That's why scientists call it microgravity, not zero gravity. Even the astronauts' movements can disrupt the environment. Ever seen a tool or a food packet drift away in the ISS? That's these subtle forces at play. So next time you see footage of astronauts flipping effortlessly in their spacecraft, remember they're not escaping gravity. They're masters of the fall, riding a cosmic current that keeps them circling Earth. And with that, let's tackle another celestial mix-up, the belief that the Milky Way is just a simple spiral. Strap in. It's more intricate than you think. Now, let's shift our gaze to one of the most mind-bending myths about the cosmos, the idea that the universe has a center. It's easy to assume that everything expands outward from a single point, like an explosion, but the reality is far stranger. Picture this: the universe is more like a loaf of raisin bread rising in the oven, with galaxies as the raisins. Here's how it works: as the bread bakes, it expands evenly in all directions. Every raisin moves away from every other raisin, not because they're being pushed from a central point, but because the dough itself is stretching. Similarly, in our universe, space itself is expanding, carrying galaxies along with it. This means no matter where you are, whether you're on Earth, a distant star, or a galaxy billions of light years away, you'd observe the same thing: all other galaxies moving away from you. This isn't just a clever analogy. Hubble's observations in the 1920s confirmed it. By measuring the light from distant galaxies, he noticed something extraordinary. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, became the cornerstone of our understanding of cosmic expansion. It showed that the universe isn't just growing, it's doing so uniformly with no privileged center. But why does this happen? Think of space as a grid that's stretching in every direction. As it expands, the distances between galaxies increase. A galaxy 1 million light-years away from us might move an extra 100,000 light-years over time, while a galaxy 2 million light-years away would move 200,000 light-years, doubling the speed. That's why distant galaxies seem to race away faster than nearby ones. Now, here's where it gets even weirder. The expansion isn't something we can see on small scales, like within our solar system or even the Milky Way. Gravity binds objects together tightly enough to resist the stretching of space. But on cosmic scales, where gravity's grip is weaker, the expansion dominates. This is why, billions of years from now, distant galaxies will vanish from our view entirely, their light stretched beyond detection. So does the universe have a center? Not in the way we typically imagine. There's no edge, no middle point, just an ever-growing expanse where every spot looks like the center from its own perspective. And with that, let's turn to another cosmic misconception, the belief that space travel makes you weightless. Get ready, it's not quite what sci-fi movies suggest. Now, let's tackle a myth that's been floating around literally. Many people believe that astronauts in space are weightless because there's no gravity up there. But here's the twist, that's not quite true. Gravity doesn't just vanish when you leave Earth. In fact, it's still very much at work, even on the International Space Station. So why do astronauts appear to float? The answer lies in a fascinating phenomenon called free fall. Imagine you're in an elevator and suddenly the cable snaps. For those terrifying seconds as you plummet, you'd feel weightless not because gravity disappeared, but because you and the elevator are falling at the same rate. That's essentially what's happening in space. The International Space Station isn't beyond Earth's gravity. It's actually in a continuous state of free fall toward our planet. But because it's also moving sideways at an incredible speed, about 17,500 miles per hour, it keeps missing the ground, creating that iconic floating effect. This is where the term microgravity comes in. It doesn't mean zero gravity. It means gravity's effects are dramatically reduced because everything is falling together. NASA even trains astronauts for this sensation using a modified airplane nicknamed the Vomit Comet. This plane flies in parabolic arcs, climbing steeply and then nosediving to create short periods of weightlessness. It's not just for fun, though it certainly looks at it's crucial for helping astronauts adapt to the conditions they'll face in orbit. But here's another layer to the myth. Sci-fi movies often show ships with artificial gravity, making it seem like weightlessness is the default in space. In reality, if you were far from any massive object, say, drifting between galaxies, you wouldn't feel weightless because of a lack of gravity. You'd feel it because there's nothing to resist your motion. Gravity's pull diminishes with distance, but it never truly hits zero. Even the moon's gravity affects tides on Earth from 239,000 miles away. So next time you see astronauts floating aboard the ISS, remember, they're not in a gravity-free zone. They're in a delicate dance with Earth's pull, falling endlessly but moving so fast they never hit the ground. And with that, let's turn our attention to another cosmic illusion, the idea that the Milky Way is just a simple spiral. What we've recently discovered about our galaxy's structure might surprise you. Here's how we'll transition into the next section, keeping the flow natural and engaging while diving into the myth about the Milky Way's structure. Now, let's unravel another cosmic misconception, one that's been painted across textbooks and documentaries for decades. Picture the Milky Way in your mind, and chances are you see a classic spiral galaxy with elegant arms curling outward like a pinwheel. But here's the twist: that image isn't just incomplete, it's outdated. Scientists have discovered our galaxy isn't a simple spiral at all. It's something far more intriguing, a barred spiral galaxy. For years, astronomers struggled to map the Milky Way's true shape because, well, we're stuck inside it. Imagine trying to sketch the blueprint of your house while standing in the hallway blindfolded. That's the challenge they faced, but thanks to cutting-edge tools like the Gaia Space Telescope and infrared surveys, we've pieced together a clearer picture. At the heart of the Milky Way, instead of a neat spiral core, there's a thick bar of stars, a straight structure stretching thousands of light years. Our solar system, it's tucked away in one of the spiral arms, orbiting this bar like a car on a cosmic roundabout. This barred structure isn't just a minor detail, it's a game-changer for understanding how galaxies evolve. Bars act like stellar traffic jams, funneling gas and dust toward the center, fueling star formation and even supermassive black holes. In fact, about 2/3 of all spiral galaxies have these bars, suggesting they're a common phase in galactic life. The Milky Way's bar might even explain why our neighborhood is so lively, with bursts of new stars and chaotic magnetic fields near the core. But the surprises don't stop there. Recent mapping efforts revealed the Milky Way's disk isn't flat. It's warped like a vinyl record left in the sun. This bending, caused by gravitational tugs from nearby galaxies and dark matter, was hidden for centuries because earlier telescopes couldn't peer through the dust clogging our view. Now, with infrared and radio astronomy, we've spotted stars and gas clouds twisting upward at the edges, giving the galaxy a subtle S-shape. So why does this myth persist? Blame artistic license. Most illustrations simplify the Milky Way for clarity, smoothing out its quirks. Even NASA's older models skipped the bar because the evidence wasn't solid until the early 2000s. But science evolves, and today's galactic portraits are richer and weirder than ever. Next time you see a spiral galaxy in a poster, remember, the Milky Way isn't just spinning gracefully. It's a dynamic, messy, barred beast with secrets we're still untangling. And speaking of cosmic oddities, let's tackle another visual illusion: the claim that you can see the Great Wall of China from the moon. Spoiler, the math doesn't add up. Now, let's tackle a myth that's been floating around for ages, one that even made its way into school books and travel brochures. You've probably heard it before: the idea that the Great Wall of China is the only human-made structure visible from the moon. It sounds impressive, but here's the reality: it's pure fiction. First, think about the numbers. The moon is roughly 238,000 miles away from Earth. At that distance, even the Great Wall, which stretches over 13,000 miles, would be incredibly hard to spot. Why? Because of something called angular resolution, the ability of the human eye or a camera to distinguish details. From the moon, the Great Wall would appear about as wide as a single human hair held at arm's length. It's simply too narrow to be visible, but don't just take our word for it. Ask the astronauts. Not a single Apollo mission crew member reported seeing the Great Wall from lunar orbit. In fact, when astronaut Alan Shepard was asked about it, he laughed and said, "No, you can't see the Great Wall from the moon. Even from low Earth orbit, where the International Space Station operates, the wall is barely visible under perfect conditions. Think clear skies, the right lighting, and knowing exactly where to look." Then there's the math. Let's break it down. The Great Wall averages about 20 feet wide. From the moon, that width translates to an angular size of roughly 0.00001 degrees. For comparison, the smallest detail the human eye can resolve is about 1/60th of a degree. The wall doesn't even come close. Cameras on the Apollo missions couldn't pick it up either. Their resolution wasn't nearly high enough. What about other structures? If the Great Wall isn't visible, what is? Surprisingly, some large cities, highways, and even airport runways can be seen from low Earth orbit because of their contrast with the surrounding terrain. But from the moon, nothing human-made is visible to the naked eye. So where did this myth come from? Blame a mix of patriotic pride and a misunderstanding of scale. The idea seems to have originated in the early 1900s, long before space travel, when people vastly overestimated what could be seen at such distances. Over time, the story stuck, repeated in classrooms and pop culture without anyone checking the facts. But science doesn't care about legends. The evidence is clear. The Great Wall is an awe-inspiring feat of engineering, but it's not a cosmic landmark. And that's okay, because the real wonder isn't about being seen from space. It's about the centuries of history, labor, and ingenuity that built it. Now, let's turn to another cosmic exaggeration, the idea that solar flares could vaporize Earth. The truth is both less dramatic and far more fascinating. Now let's shift our gaze to a myth that sounds like it's straight out of a sci-fi disaster movie, the idea that a solar flare could vaporize Earth. Hollywood loves to crank up the drama, but the reality is far less apocalyptic, though no less fascinating. First, let's clarify what solar flares actually are. These explosive bursts of energy from the sun's surface are caused by tangled magnetic fields suddenly snapping into a new arrangement. They release intense radiation, X-rays, ultraviolet light, and charged particles. But here's the key: even the most powerful solar flare couldn't turn Earth into a cosmic cinder. Why? Because the energy simply isn't concentrated enough. The sun's fury spreads out over millions of miles, and by the time it reaches us, it's more of a disruptive nudge than a planet-erasing blast. But that doesn't mean solar flares are harmless. Their real danger lies in their ability to mess with our technology. Take the Carrington event of 1859, the most intense solar storm on record. Back then, it fried telegraph systems, causing sparks to fly from machines and even igniting some papers. Fast forward to today, and a similar event could be catastrophic for our power grids, satellites, and communication networks. Imagine a world where GPS fails, transformers explode, and the internet grinds to a halt. That's the genuine risk solar flares pose. Scientists estimate the damage from a Carrington-level storm today could cost trillions and take years to fix. Then there are coronal mass ejections, or CME, often confused with solar flares but far more consequential. These are massive clouds of charged particles ejected from the sun's corona. When a CME hits Earth's magnetic field, it can trigger dazzling auroras, but it can also induce powerful electric currents in power lines, frying transformers and causing blackouts. In 1989, a CME left 6 million people in Quebec without power for 9 hours. The kicker: that was a relatively minor event compared to the Carrington storm. So why the myth about vaporization? It's a classic case of hyperbole. Movies and sensational headlines amplify the threat, but the truth is Earth's atmosphere and magnetic field shield us from the worst of the sun's tantrums. Even the most extreme solar activity wouldn't scorch the planet's surface, though it might send us back to the pre-internet dark ages for a while. The real takeaway: we don't need to fear being zapped into oblivion, but we should take space weather seriously. Agencies like NASA and NOAA monitor solar activity around the clock, giving us warnings to protect critical infrastructure. It's a reminder that while the cosmos isn't out to destroy us, it demands our respect and preparation. Next up, let's unravel a misconception about the very fabric of the universe, the idea that there are only 3 states of matter. The truth is far stranger and more spectacular. Now, let's dive into something that might shake up what you learned in school: the myth that there are only 3 states of matter. You know them: solid, liquid, and gas. But the universe loves to defy simplicity, and in reality, matter can exist in far more exotic forms, especially out there in the cosmos. First, let's talk about plasma. If you've ever seen a neon sign or a flash of lightning, you've witnessed plasma in action. It's often called the 4th state of matter, and it's everywhere in space. Stars, including our Sun, are basically giant balls of plasma superheated gases where electrons are ripped away from atoms, creating a soup of charged particles. In fact, over 99% of the visible universe is made of plasma, from the fiery surfaces of stars to the vast stretches of interstellar gas. Even the mesmerizing auroras dancing near Earth's poles are caused by solar plasma colliding with our atmosphere. But plasma isn't the only oddball out there. Enter the Bose-Einstein condensate, a state so bizarre it sounds like science fiction. Predicted by Satyendra Nath Bose and Albert Einstein back in the 1920s, this form of matter only exists at temperatures just a hair above absolute zero, the coldest possible temperature. At these extreme conditions, atoms slow down so much that they merge into a single quantum entity, behaving like one giant superatom. Scientists first created this in labs in the 1990s, but similar conditions might exist in the freezing depths of space, particularly in the cores of neutron stars or the cold vacuum between galaxies. Now, why does this myth persist? Partly because solids, liquids, and gases are the states we encounter daily, but space isn't bound by earthly norms. Take neutron stars, for example. Their cores are so dense that atoms collapse into a sea of neutrons, forming a state called neutron degenerate matter. Or quark-gluon plasma, a primordial soup that existed microseconds after the Big Bang and can now be recreated in particle colliders. These states might not be household names, but they're critical to understanding the universe's most extreme environments. So next time someone says matter only comes in three forms, you'll know better. The cosmos is a laboratory of bizarre and wonderful states, each with its own rules. And who knows, as we probe deeper into space and refine our experiments, we might discover even stranger forms of matter lurking in the shadows of the universe. Speaking of cosmic oddities, let's tackle another head-scratcher, the myth that the moon's phases are caused by Earth's shadow. The truth is just as fascinating, but for entirely different reasons. Now, let's clear up one of the most persistent misconceptions about our nearest celestial neighbor, the idea that the moon's phases are caused by Earth's shadow. It's an easy mix-up to make, but the real explanation is even more fascinating. First, imagine the moon as a giant space mirror. Its phases aren't about shadows at all, they're about sunlight and angles. The moon doesn't produce its own light. Instead, it reflects sunlight just like a bicycle reflector glows when a car's headlights hit it. As the moon orbits Earth, the angle between the sun, Earth, and moon changes, revealing different portions of the moon's sunlit half to us. When the moon is between the sun and Earth, we see the fully lit side, that's the bright, round face of a full moon. When the moon is on the opposite side of Earth from the sun, sunlight hits its far side, leaving the side facing us in darkness, which we call a new moon. The crescent, quarter, and gibbous phases, those are just in-between stages as the moon cycles through these positions over about 29.5 days. But wait, what about lunar eclipses? That's where Earth's shadow actually comes into play. Unlike phases, eclipses are rare, dramatic events. During a lunar eclipse, Earth moves directly between the sun and the moon, casting its shadow onto the moon's surface. Instead of the usual silvery glow, the moon can turn a deep reddish color, often called a blood moon, because Earth's atmosphere bends sunlight, filtering out blue light and letting red pass through. It's like the entire planet is projecting a sunset onto the moon. Here's a quick way to remember the difference. Phases happen every month like clockwork, while eclipses are special, occasional performances. If you see a crescent moon in the sky, that's not Earth's shadow, it's simply the angle of sunlight. But if the entire moon dims and turns coppery red, now you're witnessing Earth's shadow in action. Why does this myth stick around? Probably because both phenomena involve changes in the moon's appearance, but the mechanics couldn't be more different. One is a slow dance of sunlight and geometry, the other a celestial alignment with Earth playing the lead role. Next time you gaze up at a waxing gibbous moon, remember, it's not hiding in Earth's shadow. It's just showing you a different angle of its sunlit face, a cosmic reminder of how perspective shapes what we see. And speaking of cosmic tricks of the eye, let's tackle another myth that's been circulating for decades, the idea that Saturn is the only planet with rings. Turns out our solar system loves accessorizing. Now, let's set the record straight on a dazzling myth. Saturn isn't the only planet in our solar system with rings. While its iconic, photogenic rings steal the spotlight, Jupiter, Uranus, and Neptune have their own subtle but stunning ring systems too. Take Jupiter, the solar system's giant. When the Voyager 1 spacecraft flew past it in 1979, it captured something unexpected, a faint, dusty ring around the planet. Unlike Saturn's icy, gleaming rings, Jupiter's are made mostly of dark, rocky particles, likely debris from micrometeorite impacts on its moons. These rings are so delicate they're almost invisible from Earth, requiring powerful telescopes or close-up spacecraft images to spot them. But they're there, a whisper-thin halo around the gas giant. Then there's Uranus, the sideways planet. Voyager 2 revealed its rings in 1986, and they're unlike anything else in our solar system. Instead of circling the planet's equator like Saturn's, Uranus's rings are tilted almost perpendicular to its orbit, following the planet's extreme axial tilt. Scientists think these narrow, dark rings might be remnants of shattered moons or collisions between smaller bodies. What's even cooler, some of these rings have shepherd moons, tiny satellites that herd the ring particles, keeping them in line like cosmic sheepdogs. Neptune's rings, also discovered by Voyager 2, are even more mysterious. They're patchy and uneven, with clumps of dust called arcs that shouldn't exist according to orbital mechanics. Normally, ring particles should spread out evenly over time, but Neptune's arcs defy expectations. One theory suggests the gravity of nearby moons like Galatea traps the debris in these dense clusters, creating a celestial puzzle we're still solving. So why does Saturn get all the attention? Its rings are simply the most spectacular, bright, broad, and made mostly of reflective ice chunks that can be as small as dust or as large as houses. But the other gas giants prove that ring systems come in all flavors, from Jupiter's faint dust bands to Uranus's tilted ribbons and Neptune's clumpy arcs. The next time you see Saturn through a telescope, remember, it's not the only ringed world in town. Our solar system is full of hidden gems, and sometimes the quietest ones have the most fascinating stories. Speaking of hidden wonders, let's tackle another myth that's been floating around, the idea that the Big Bang was an explosion. The truth, it's far more mind-bending than that. Here's the script section for Myth 24, seamlessly continuing from the previous segment. Now, let's unravel one of the most misunderstood ideas in cosmology, the Big Bang. Despite what the name suggests, it wasn't an explosion in the traditional sense. Picture this: instead of a fiery blast radiating outward from a single point, the Big Bang was the rapid expansion of space itself, stretching the universe from an incredibly hot, dense state into the vast cosmos we see today. The key difference: an explosion, like a firework, has a center and sends debris flying into pre-existing space. But the Big Bang didn't happen in space, it created space. There's no central point or edge to the universe because every region of space was, and still is, expanding uniformly. Think of it like dots on an inflating balloon. As the balloon grows, every dot moves away from every other dot, but no dot is the center of the expansion. This idea ties into cosmic inflation, a theory that explains how the universe expanded exponentially in the first fraction of a second after the Big Bang. Inflation smoothed out the early universe, creating the remarkably even distribution of matter we observe in the cosmic microwave background, the faint afterglow of the Big Bang. Without inflation, we wouldn't have the large-scale structure of galaxies and voids we see today. So why do so many people imagine the Big Bang as a colossal explosion? Blame pop culture and misleading analogies. Movies and diagrams often depict it as a chaotic burst from a single location, but that's a simplification. In reality, the universe's expansion is more like a loaf of raisin bread baking in the oven. As the dough rises, every raisin moves farther apart, but no raisin is the starting point. Here's another twist. The Big Bang wasn't even a one-time event. Space is still expanding today, carrying galaxies away from each other. And because this expansion is accelerating due to dark energy, distant galaxies will eventually fade from view entirely. The next time someone describes the Big Bang as an explosion, you'll know the truth. It's not about fireworks or shockwaves, but the breathtaking stretch of spacetime itself. And speaking of cosmic stretching, let's tackle another myth that bends the mind: the idea that astronauts train underwater to experience zero gravity. The reality, it's not quite what you think. Now, let's dive into a myth that's floated around for decades: the idea that astronauts train underwater to experience zero gravity. While it's true that NASA and other space agencies use giant pools like the Neutral Buoyancy Lab to prepare for spacewalks, the reality behind this training is far more nuanced than simply simulating zero-G. Here's the key difference. Underwater training achieves neutral buoyancy, where astronauts neither sink nor float, making them feel weightless. But this is not the same as the microgravity experienced in orbit. In space, astronauts are in a continuous state of free fall, where gravity is still acting on them, just like the International Space Station, which is constantly falling toward Earth but moving sideways fast enough to miss it. Underwater, however, gravity is still very much present. You're just countering it with buoyancy, which creates a different set of physical sensations and limitations. For example, underwater movements are sluggish due to water resistance, something you don't deal with in space. Try waving your hand in a pool versus doing the same on the ISS. The drag in water makes every motion slower and more effortful. This means astronauts have to adapt their movements all over again once they're actually in microgravity. Another limitation: neutral buoyancy doesn't perfectly replicate the way objects behave in space. On the ISS, tools and equipment float freely unless tethered, but in water, they either sink or float to the surface unless carefully balanced. This discrepancy forces astronauts to mentally adjust between training and the real thing. So why use water at all? Because it's the best Earth-bound option for practicing spacewalks. Floating in a pool lets astronauts rehearse complex tasks like repairing equipment or assembling structures while wearing bulky spacesuits. It's about building muscle memory and problem-solving skills, not mimicking zero-G perfectly. But there's another method closer to true microgravity: parabolic flights, aka the vomit comet. These specially designed aircraft fly in steep arcs, creating short bursts of weightlessness about 20 to 30 seconds at a time. It's not practical for long training sessions, but it gives astronauts a taste of real free fall dynamics. The bottom line: underwater training is a brilliant workaround, but it's not a magic portal to zero-G. It's like rehearsing a play in your backyard instead of on Broadway, helpful for learning lines, but nothing compares to the real stage. And speaking of stages, our next myth takes us to the red planet, where viral claims insist Mars appears as big as the moon in our sky. Time to set the record straight. Now, let's tackle a myth that resurfaces like clockwork, especially when Mars makes its closest approach to Earth. You've probably seen those viral posts claiming Mars will look as big as the moon tonight. It's a jaw-dropping headline, but here's the reality: it's pure fiction. Let's break down why this claim doesn't hold up to basic astronomy. First, the science of apparent size. How big an object appears in our sky depends on its angular diameter, the angle it takes up from our viewpoint. The moon, for instance, spans about half a degree, roughly the width of your pinky finger held at arm's length. Mars, even at its closest, has an angular diameter around 1/75th of that. To put it plainly, Mars would need to be 75 times larger in the sky to match the Moon's size. That's not just a small difference, it's like comparing a golf ball to a grain of sand. Why does this myth persist? Every 26 months or so, Mars reaches opposition when Earth laps it in their orbits, bringing the two planets closest. In 2003, Mars came within 35 million miles of Earth, its nearest approach in 60,000 years. Even then, Mars was still a tiny red dot, barely noticeable without a telescope. Social media posts often exaggerate these events, stripping away context to make them seem miraculous. Here's a fun experiment. Next time you see Mars in the night sky, hold up your pinky. The Moon comfortably covers it, but Mars, you'd need a magnifying glass to even spot it against your fingertip. Even at opposition, Mars shines brightly, but its angular size remains minuscule. Telescopes reveal its disk, but to the naked eye, it's just another star-like point. The myth's origins trace back to a 2003 email chain that misquoted an astronomer's comparison. They'd said Mars would look as large as the Moon through a telescope at 75 times magnification, but the "through a telescope" part got lost in translation. The internet ran with the sensational version, and the myth snowballed. So why can't Mars ever appear Moon-sized? Orbital mechanics. For Mars to match the Moon's angular diameter, it would need to be less than 500,000 miles from Earth, closer than any planet has ever been. At that distance, its gravity would disrupt Earth's tides, orbits, and possibly even trigger geological chaos. Safe to say, if Mars were that close, we'd have bigger problems than viral misinformation. The next time this claim pops up, you'll know the truth. Mars is fascinating. Its storms, canyons, and potential for life make it worthy of attention. But its size in our sky, that's one marvel we don't need to exaggerate. And speaking of cosmic illusions, our next myth takes on the Van Allen belts, those radioactive zones some say make space travel impossible. Time to separate fact from fiction. Now, let's turn our attention to another cosmic misconception, one that's been used to cast doubt on some of humanity's greatest achievements. You might have heard claims that the Van Allen belts, those donut-shaped zones of radiation surrounding Earth, are utterly impassable, making space travel a hoax. But here's the truth. Not only did NASA Apollo missions safely navigate these belts, but scientists have also developed ingenious ways to minimize the risks. Let's dive into how they did it. First, what are the Van Allen belts? Discovered in 1958 by James Van Allen, these regions are packed with charged particles trapped by Earth's magnetic field. There are two main belts, the inner belt packed with high-energy protons and the outer belt swirling with electrons. They're not exactly a friendly environment. Prolonged exposure could be hazardous to astronauts and electronics alike. But impassable, far from it. The key lies in trajectory and timing. During the Apollo missions, NASA plotted courses that minimized time spent in the most intense radiation zones. By launching quickly and angling their trajectories just right, astronauts zipped through the thinner edges of the belts in under an hour. Think of it like sprinting through a brief rain shower rather than standing in a downpour. Total radiation exposure, less than a routine medical X-ray. Then there's shielding. Apollo spacecraft weren't armored like tanks, but they weren't defenseless either. Aluminum hulls absorbed lower energy particles, while onboard monitoring systems tracked radiation levels in real time. Mission planners even scheduled lunar voyages during periods of lower solar activity when the belts were quieter. It's a testament to engineering foresight, not luck. But what about the myth's persistence? Critics often point to the belt's peak intensities, ignoring how sharply radiation drops off just outside those zones. It's like claiming a mountain is unclimbable because you're only looking at its summit. Modern satellites and the International Space Station routinely operate within the belt's outer reaches, protected by careful design and materials. Even SpaceX's Crew Dragon and NASA Orion capsule incorporate advanced shielding for deep space travel. Here's the kicker: the Apollo missions weren't silent on this. They carried radiation dosimeters and the data matched predictions perfectly. Later missions like the Van Allen probes mapped the belts in detail, confirming their structure and variability. If the belts were truly impassable, how did those probes and astronauts return unharmed? So why does this myth endure? It preys on the unfamiliar. Radiation sounds scary and space travel is risky, but not for the reasons conspiracy theorists claim. The real marvel isn't that we cheated physics, it's that we understood it well enough to dance through the danger. And speaking of cosmic dangers, our next myth tackles another extreme: the idea that space is always freezing cold. Time to warm up to the facts. Now, let's shatter another icy misconception: the idea that space is uniformly freezing cold. While it's true that the cosmic void lacks an atmosphere to trap heat, temperatures out there are anything but consistent. Picture this: you're floating near Mercury, the closest planet to the Sun. On its sunlit side, surface temperatures soar to a blistering 800 degrees Fahrenheit, hot enough to melt lead. But step into the shadows and you'd plummet to minus 290 degrees Fahrenheit, colder than Antarctica's deepest freeze. That's a swing of over 1,000 degrees, all on one small world. So why the extreme swings? It all comes down to atmosphere, or rather, the lack of one. Earth's thick blanket of air distributes heat globally, smoothing out temperature extremes. But where there's no atmosphere, like on the Moon or Mercury, there's nothing to scatter or retain warmth. Sunlight hits surfaces directly, baking them to extreme highs, while shaded areas radiate heat into space almost instantly, plunging into deep freezes. Even spacecraft face this wild ride. The Hubble Space Telescope, for example, orbits Earth every 90 minutes, cycling between scorching sunlight and frigid darkness. Engineers had to design its components to withstand these rapid shifts without cracking or failing. Then there's the Goldilocks effect of distance. Mars, farther from the Sun than Earth, averages a chilly minus 80 degrees Fahrenheit. But during summer near its equator, midday temps can reach a balmy 70 degrees, almost comfortable for a human in a spacesuit. Meanwhile, gas giants like Jupiter, with their turbulent atmospheres, generate internal heat from gravitational compression, making their upper layers frosty while their cores simmer at tens of thousands of degrees. Here's where it gets even wilder. The very definition of cold in space changes depending on what you're measuring. The cosmic microwave background, the afterglow of the Big Bang, chills the universe to minus 455 degrees Fahrenheit. Yet, in the emptiness between galaxies, there's barely any matter to have a temperature. Conversely, nebulous cosmic clouds of gas can be superheated by nearby stars glowing at thousands of degrees. The takeaway: space isn't a monolithic freezer. It's a dynamic arena where temperatures swing from forge-like to cryogenic, sometimes within miles of each other. And that brings us to our next celestial puzzler, one that involves not just temperature, but the delicate dance between Earth, the Moon, and the Sun. Now, let's wade into another cosmic misconception: the idea that the Moon alone controls Earth's tides. While our lunar neighbor plays the starring role, the Sun is a powerful supporting actor in this gravitational drama. Here's how it works. The Moon's gravity tugs on Earth's oceans, creating bulges of water on the side closest to it and the side farthest away. These bulges are what we experience as high tides, with low tides occurring in the areas between them. But the Sun, despite being much farther away, exerts its own gravitational pull, one so strong it can amplify or soften the Moon's effects. When the Sun, Moon, and Earth align during new and full moons, their combined gravity creates spring tides, the highest high tides and the lowest low tides of the month. Picture the ocean being stretched between these two celestial giants, with water levels rising and falling more dramatically. Conversely, during first and third quarter moons, when the Sun and Moon form a right angle relative to Earth, their gravitational forces partially cancel each other out. This results in neap tides where the difference between high and low tide is much subtler. It's like a cosmic tug of war where neither side wins decisively. But the Sun's influence doesn't stop there. Earth's elliptical orbit means our distance from the Sun changes throughout the year. When we're closest to it around January in a phenomenon called perihelion, the Sun's gravitational grip intensifies, making spring tides even more extreme. Similarly, seasonal shifts in Earth's tilt can alter how tides behave along coastlines. For example, during equinoxes, when sunlight hits the equator directly, tide-generating forces are maximized, leading to more pronounced tidal ranges. Coastal geography also plays a surprising role. Narrow bays and inlets can funnel incoming tides, creating dramatic surges like the infamous tidal bores of China's Kiantang River, where waves race upstream at nearly 25 miles per hour. Meanwhile, places like the Mediterranean Sea, with their limited connection to open oceans, experience barely noticeable tides. So next time you hear that the moon alone rules the tides, remember, it's a celestial collaboration. The Sun's subtle but steady hand shapes our seas just as much as the moon's, proving that even in space, teamwork makes the dream work. And speaking of cosmic partnerships, our final myth takes us from the tides to the pyramids, where some believe another kind of force left its mark. Now, let's tackle one of the most persistent space-inspired myths of all, the idea that extraterrestrials built the pyramids. This theory has captured imaginations for decades, fueled by sensational documentaries and viral conspiracy theories. But when we turn to the actual evidence, the truth is far more fascinating and human. Archaeologists have uncovered overwhelming proof that the ancient Egyptians constructed the pyramids using ingenious engineering, not alien technology. For starters, worker settlements near the Giza Plateau reveal thousands of bones, tools, and even ancient payroll records, evidence of a highly organized labor force. These builders weren't slaves but skilled workers who took pride in their craft, as seen in meticulous carvings and burial sites honoring their contributions. The famous limestone blocks, they were quarried locally and transported using ramps, sleds, and waterways, methods confirmed by erosion patterns and ancient texts. Even the precision of the pyramid's alignment with stars can be explained by the Egyptians' advanced understanding of astronomy, honed over centuries of observation. Then there's Occam's razor, the principle that the simplest explanation is usually the correct one. Claims of alien intervention require a leap of logic. Why would advanced beings cross light years just to stack rocks, then vanish without leaving behind any other definitive technology? Meanwhile, human ingenuity fits all the facts without inventing interstellar architects. Take the Great Pyramid's air shafts, once thought to be evidence of alien blueprints. Researchers later realized they aligned with specific stars for spiritual reasons, reflecting the Egyptians' belief in connecting the pharaoh's soul to the cosmos. Even the pyramid's near-perfect proportions have earthly origins. The golden ratio, often cited as proof of alien design, appears in nature from seashells to sunflower spirals, suggesting the Egyptians simply mimicked patterns they admired. And let's not forget the trial and error visible in earlier pyramids, like the Bent Pyramid, whose design flaws show a civilization learning through experimentation. As for the myth's endurance, blame pop culture more than science. From 1970s UFO fever to modern viral clickbait, the alien pyramid narrative thrives on mystery, not evidence. But the real story of a civilization achieving the impossible with copper tools and collective effort is far more inspiring. After all, why credit aliens when humanity's own brilliance is this undeniable? And with that, we've reached the end of our cosmic myth-busting journey. But before we wrap up, let's revisit some of the most surprising truths we've uncovered along the way. Now, as we bring this cosmic myth-busting adventure to a close, let's take a moment to reflect on some of the most jaw-dropping revelations we've uncovered together. Remember when we debunked the idea that the dark side of the moon is always dark? Turns out sunlight dances across every inch of the lunar surface. It's just tidally locked, giving us only one view from Earth. Or how about the myth that meteorites land scorching hot? In reality, they often freeze during their journey through space and stay cold long after hitting the ground. And let's not forget the wild claim that space is completely silent. While sound waves can't travel in a vacuum, planets like Saturn emit eerie radio emissions that scientists can convert into spine-tingling soundscapes. But perhaps the biggest takeaway here is how easily pop culture twists space science into sensational fiction. From Hollywood's fiery asteroid explosions, which ignore the reality of cold, slow-moving space rocks, to viral memes claiming Mars will appear as large as the moon, misinformation spreads faster than light. That's why it's so important to stay curious and question what you hear. After all, space is mysterious enough without adding myths to the mix. So, which myth surprised you the most? Was it learning that black holes aren't cosmic vacuum cleaners but behave like massive stars? Or discovering that astronauts don't actually float in zero gravity, they're in a constant state of free fall around Earth? Drop your favorites in the comments below and let's keep the conversation going. And if you enjoyed this deep dive into space truths, don't forget to hit that like button, subscribe for more mind-bending science, and ring the notification bell so you never miss a cosmic revelation. Thanks for joining me on this journey through the stars where the facts are often stranger than fiction.